Flipped classroom video for Maths AS Unit 2. The constant acceleration equations, Part 1. Constant acceleration equations. Suppose we have a particle that's moving on a straight line with constant acceleration, a, meters per second squared, in such a way that initially it is at a point O on the line and moving with velocity u, meters per second, and at time t it is at a displacement s, meters from O and moving with velocity v, meters per second. So there we have a diagram. At time naught, t is naught, it's at position 0 and moving to the right with velocity u, meters per second. At time t equals t, it is at a point with a displacement s from O and velocity v and acceleration, which has two heads, if you notice, an arrow with two heads for acceleration, a, meters per second squared. As a convention, double-headed arrow will be used to indicate accelerations and a single-headed arrow for velocities. S is just the displacement. Consider the velocity time graph. I'll show that one. For the particle, we know that the acceleration or gradient is going to be constant and that the initial velocity of the particle is u. The graph is therefore a straight line of gradient a and v-intercept crossing the v-axis at the point u. So recalling that the equation of a graph which is a straight line of gradient m and y-intercept c is y equals mx plus c, we can deduce that the equation of the velocity time graph is v, which is our y, equals a is our gradient, plus u, which is our y, v-intercept. So v equals at plus u, which is usually written as v equals u plus at. So that is our first constant acceleration equation. The displacement of the particle from O at a time t is denoted by s, and the formula for this can be deduced from the fact that the displacement is the area under the velocity time graph. And we have here a trapezium on its side, and the area of the trapezium is the sum of the parallel sides times the distance between them and divide by 2. So half of u plus v times t is our s. So there's our second equation of constant acceleration equation. So s is equal to half u plus v times t. So there's 2 we've got. Now we can rearrange some of these and get the others. Using equation 1 to substitute for v in 2. Instead of v in 2, I am putting u plus at. So multiply the t, so add the 2 u's, then multiply the half and the t into that equation, and we've got s is equal to ut plus a half at squared. So there's our third equation of motion. Equation 1 can be written as u equals v minus at. So we're going to substitute for the u in equation 2. So giving us an equation with no u in it. Collecting terms, multiplying the bracket out, and we get s equals vt minus a half at squared. So there's our fourth equation of motion. Sometimes this is not given to you, but it's worth using it. So you've got an equation for each of the terms, and then you can pick out which one you need. Equation 1 can be rewritten as t equals. So t equals v minus u, all divided by a. Substitute that into equation 2, and we get s is equal to half u plus v times by v minus u divided by a. Now u plus v times v minus u There's an imaginary bracket around that. Gives us a difference of 2 squares. So if I multiply by 2a on the left, so I got 2as equals 2 brackets, which gives us a difference of 2 squares. So v squared minus u squared. So rearranging that, and we get v squared equals u squared plus 2as. And that's our fifth equation of motion. Now, each of these equations, you're usually given 3 items of knowledge about what's happening, and then you can find a fourth. So each of these equations would be missing one of the terms. Now, this one is missing s, this one is missing a, this one is missing v, that one is missing u, and this one is missing t. So you've got an equation for each situation. These 5 equations are known collectively as the constant acceleration equation. But there's some debate, if you do physics, whether the displacement should be represented by s or by x. So you might meet the constant acceleration equations as x for displacement. And there you have those as well. That gives you an introduction to the 5 constant acceleration equations.